So in this video, we're going to be looking at exactly how to apply this REO trick to help us determine the relative stability of conjugate bases, which will ultimately be used to determine the strength of acids without using pKa values. So with this REO trick, the 4 steps, atoms, resonance, induction, and orbital, we take them in order, which means that the very first thing that we look at when we're comparing two conjugate bases is the atom that bears the negative formal charge. That's our first step. So number 1, compare the atoms with the negative formal charge. And if the atoms are both in the same row on the periodic table, the atom that's more electronegative is the one that's more stable. And this makes sense because the more electronegative atom is going to be the one that's more comfortable bearing the negative formal charge. And so therefore, the conjugate base that has the more stable negatively charged atom is going to be the more stable conjugate base. So that would be something like if we were comparing the relative stability of this versus this. In these two bases, the negative formal charge is on the nitrogen, the negative formal charge is on the oxygen. Both of those atoms are in the same row on the periodic table. Oxygen is the more electronegative atom of the two, which means that this base is more stable than this base. And therefore, the acid that produced this conjugate base is more acidic than the acid that produced this conjugate base. You can also compare atoms if they're in the same column on the periodic table. And in that particular case, the larger atom is the one that's most stable. This is because the larger the atom is, the more surface area the atom has, and the more it can spread out or delocalize the negative charge over the whole entire atom. So this is actually kind of reverse of what we see up here, because the larger atom is going to be lower on the periodic table and therefore less electronegative. But because of the size and the ability to distribute that charge over a larger area of space, that's what gives rise to stability. So if we're comparing this versus this, these two, sulfur and oxygen being in the same column, sulfur is larger than the oxygen atom, which means that this base is going to be more stable than hydroxide, and therefore the acid that produced this conjugate base is going to be a stronger acid. So this is the very first thing that you're going to look at when you're comparing conjugate bases and trying to determine their stability. And if this rule doesn't apply, like it would not have applied in this example up here, bromine versus carbon, not in the same row, not in the same column, rule number 1 doesn't apply, then you move on to rule number 2. And rule number 2 is to draw resonance structures. And as you learned in the last chapter, in chapter 2, the more resonance structures you can draw, even if they're not good, the more stable the structure is. So you're going to look at all resonance structures. I had a hard time spelling that. And the conjugate base that has the most resonance structures is the one that's most stable. And that's a pretty simple concept. So I'm not going to give you examples of that. But you're gonna take your bases, you're gonna draw out resonance structures, you're gonna compare how many resonance structures can I draw for the two conjugate bases. The one that gives you the most resonance structures is the most stable base, and therefore it came from the strongest acid. If that doesn't apply, and most of the time rule 1 or 2 is going to apply. But if rule 1 and 2 doesn't apply, then you're going to move on to rule number 3, which is induction. Induction is really similar to delocalization. It is the withdraw or the pulling of electron density. This comes from having electronegative atoms that are somewhere in the vicinity of the negative formal charge. And those electronegative atoms, because of their electronegativity, are going to pull on the electron density, and they're going to delocalize it in their direction and spread it out. And this is a good thing. So if you have electronegative atoms that are located away from the position of the formal charge. So this is not where the formal charge is sitting. They're going to stabilize the compound. And when we talked about delocalization, we talked about how that's a good thing when we were looking at it in terms of resonance, the ability to move that charge, in this case the negative charge, spread it out over more than one atom. This is a good thing for the molecule. So let's consider, for example, this conjugate base versus this base. They both have the same oxygen atom bearing the formal charge, and they both are going to have the same number of resonance structures if you draw it out. The only difference between these two atoms is, between the two compounds is the presence of the chlorine atom. Chlorine is electronegative, and because of that, it's going to suck the electron density in its direction. It's going to spread it out over the molecule, and that's going to increase the stability of this base relative to this base. So this is going to be a more stable base, and therefore the acid that produced this base is going to be stronger than the acid that produced this base. And we see it's an additive effect. So the more electronegative atoms you have, more in terms of quantity, the more stable things are going to get. So this compound over here, this base, is going to be even more stable than this base, which will be even more stable than that one. So this one would be the most stable, and therefore the acid that produced this base would be the strongest acid. And this one would be the least stable. And almost always, these first 3 rules are going to work in helping you predict the stability of a conjugate base. But if they don't, if you need to keep going, then rule number 4 tells you to compare the orbitals of the atom with the negative formal charge. And we're going to be looking at, is it sp versus sp2 versus sp3? And again, this is just looking at the atom with the negative formal charge. The sp orbital is the most stable. of those 3 orbitals, and the sp3 is the least stable. And the reason for this is that the sp orbital is stubbier, it's rounder and shorter. So the electrons that are in an sp orbital are held more closely to the nucleus, and therefore they're sort of stabilized by the positive charge of the protons that are in the nucleus. So if you're comparing these 3 bases, this particular carbon atom with the negative formal charge is an sp3 carbon atom, this is an sp2 carbon atom, and this is an sp carbon atom. Therefore, this would be the most stable base, and this would be the least stable base. And that means that this one came from the strongest acid, and this one came from the weakest acid, and this one came from something in between. So again, what you want to do is apply these 4 rules in order. You're going to start by looking at the atom that bears a negative formal charge, and if that doesn't help you determine, then you're going to go to drawing resonance structures, and if that doesn't work, you're going to think about electronegative atoms and their inductive effect, and if that doesn't work, then you're going to look at the orbitals. And once you've practiced this a bit, then it's going to be a pretty easy process for you to use, and you'll find that it's a lot faster than looking up Kas or pKas. So in order to make sure you get plenty of practice with this concept, I want you to do skill builders 3.5 through 3.9. He's got 1 skill builder for each one of these different things, and a lot of problems. 13, 14, 45, 47, 51, 53, 15, 16, 17, 46, 18, 19, 20, 21, 22, 23, 24, 25, 26, I'm realizing that I could have said 18 through 28. There you go. And your study question for this material is, how do you predict the stability of a conjugate base?